Okay, now we need to talk about the law of universal gravitation. Okay? So, why do objects fall? Right? Ancient Greece said it was in the nature of them to float or sink or whatever. Galileo said it was a force of attraction. Einstein said the curvature is space-time. Whatever. The important thing that we know is that gravity affects all objects with mass. Okay? It's a long-range force, so the distance must also affect them. Okay? Remember, and this is very important, the force of gravity, or weight, is measured in newtons. The mass is measured in kilograms. Way too many times do kids get these two ideas mixed up. And that's very common because when people say in the United Kingdom, how much do you weigh, they usually answer in kilograms. But they're wrong. Okay, weight is something measured in newtons. And mass is something measured in kilograms. Okay, the force of gravity is proportional to the mass of the two objects, which means the larger the masses, the larger the force. Okay, the force of gravity is proportional to 1 over r squared, or inversely proportional to the distance, which means the larger the distance, we get a much smaller force. Now notice, because it's r squared, if we get a larger distance, it's not just a smaller force, it's a much smaller force. Okay? So, adding in the constant that kind of simplifies the equation out, we end up with the fact that the force of gravity is always equal to this constant, 6.67 times 10 to the negative 11th, times the mass of the one object times the mass of the other object, divided by the radius of the object squared. Okay? So finding g, we remember that Fg equals m times little g, but now we know the real answer, Fg equals gmm over r squared, where r is the distance. Well, then that means that if we kind of take this and set them side by side, we get mass of the object times little g equals g mass of the object times mass of the earth times r squared. So little g is just g m of the earth over r squared. Okay, so that's an important equation that we'll need as well. This equation and this equation. So we can do our little g for each of these different planets and plug them in. So what is this going to look like? Well, if little g equals big G times m over r squared, that means that my little g equals my big G, which is 6.67 times 10 to the negative 11th times my mass, which in the sun's case is 2.0 times 10 to the 30th, all divided by 6.96 times 10 to the 8th in parentheses squared. Okay, so I put that in my calculator just like that. Okay, so 6.67 times 10 to the negative 11th times 2.0 times 10 to the 30th divided by parentheses 6.69 times 10 to the 8th and parentheses squared, and I get, I'm going to change this back into a normal mode, and I get 298. Okay, I think I did something wrong there. Oh, I did 6.69. I should have won 6.96. Oops. So there we go. We get 275, which, since we only had two significant figures, rounds to 280. Now you can do the same thing for all these, and you'll find, not surprisingly, on the Earth, it's 9.8, which we already know. We round 10, usually. On the Moon is 1.6, on Mars 3.7, on Jupiter is 25. Okay? So, it's important to remember that it's proportionate, right? If you double the mass, how does the gravitational force change? Well, if I take my original equation and instead I double the mass, then I can rearrange the numbers, bring this 2 out front, and get 2 times gmm over d squared, which is the same as force of gravity. So it's 2 times the force of gravity. Okay. Now what happens if I double the distance? Well, then again, it's gmm over twice the distance squared. But since the squared distributes out to the d and to the 2, that simplifies to gmm over 4 times d squared. And again, if you just take this stuff, then that is just the force of gravity, so it's going to be 1/4 the force of gravity. So notice doubling the distance made the gravity 1/4 as big, not half as big, because it's squared. Okay, the radius of the Earth is such and such, and here is this mass of mass of the Earth and the mass of the spacecraft. At the Earth's surface, what is the weight of the spacecraft? Okay, so at this point what we need to do is we need to say, get our calculator out, and we do our big G, gmm over d squared, right? In this case, G, not this case, all cases, G is 6.67 times 10 to the negative 11th times mass of the Earth is 6 times 10 to the 24th times the mass of the spaceship, 7.2 times 10 to the 3rd divided by parentheses the radius, 6.38 times 10 to the 6th, and remember you have to square that, and so we find out that this thing weighs 70789 on the surface of the Earth. But if we double the distance, I can even just go straight in here and insert a 2 times the distance. Okay, then suddenly the weight drops down to 17,697. I also could have taken that number and divided by 4, and it would have given me that number. Okay, 3 times the distance of the Earth. This number should be right here, and this number should be right there. 3 times the distance of the Earth. I go in and I just change that to a 3 times the radius of the Earth. And then I get as small as 7865, which is 1/9 of the weight. Okay, so that's kind of how you use the equation. You just plug stuff in, you figure stuff out. Good luck.